All right, we're ready to get started. So today we are going to continue our discussion of mental analysis. We're going to come up with some illustrations of dimensionless numbers. So we're going to get some dimensionless numbers that we will not deal with physics of the physics of multiple class. Aside from Reynolds number, and I guess Freud number will talk about as well. But the key thing I want to get across with the video that we'll look at today is each of these dimensionless numbers we can think of as a ratio of two things. This is important concept. So we'll look at the end. We'll look at Reynolds number, which is essentially the ratio of inertia and viscosity. We'll talk about that on Wednesday. That's going to come up in our discussions of turbulence and internal and external flow. The next couple chapters, that's great. But really, any of these non-dimensional numbers you can think of as basically the ratio of how important one thing is relative to another. So again, Newton's number, we think of it as the ratio of its molecular spacing to the size of our system, right? That's how big is the spacing between molecules relative to the size of the thing we're looking at. Same is true of all the dimensionless numbers that you'll see. All these dimensionless being numbers. And we will again we will talk about it. And you'll notice the same is also going to be true of the number of seen trend. Right. So essentially these dimensionless numbers offer us a way of measuring the importance of one type of physics relative to another type of physics. So let's see some examples. So we're going to start with this Freud number, u squared over GL, so under the u over square root of GL, both are dimensions. But it basically describes the effect of inertia over the effects of gravity. Right, so it's again how much inertia the fluid has relative to how much gravitational forces affects that fluid. And it's really important for understanding how waves behave. So we'll see an example of that in this video.
On fluid flow. Here's the derivation of Freud's number. We take inertial force to equal mass times acceleration, and gravitational force to equal mass times gravitational acceleration. Remember, mass is equal to density times volume. By breaking down the components in the manner seen and plugging them into Freud's definition from earlier, we get that Freud's number is equal to the velocity of the wave divided by the square root of depth times gravitational acceleration.
I just want to stop for a second here. So we derive Reynolds number, right? We said it's the rate, the influence of inertia over viscosity by applying mental analysis to the Navier-Stokes equation. And actually, if you notice when we did that, we bumped the gravitational term into the pressure. So that would be bump gravity into pressure. If we had not done that, actually the support number would have popped out of our derivation. We've got two dimensional groupings, Reynolds number and support. But this is another way of deriving or thinking about these dimensional numbers, which is basically they're taking something having to do with the inertial force, right? So the inertia of the fluid, NA, and taking that relative to the gravitational force. These things have the same dimensions right? We're gonna call it dimensions number by thing greater. And then if we do that, then we just take, in this case, MA over MG. And we'll end up with the, graph. So we can get at it a couple of different ways, right? Get it from dimensional analysis. If we said, we could set up a problem where we have, some number of variables, right? And we do the pi theorem thing. We can come up with the crowd number that way as well. But this is just another way of thinking about these dimensions numbers.
When Freud's number is less than 1, it is classified as subcritical and indicates that a wave on the surface of a fluid moves upstream. When Freud's number is more than 1, it is supercritical and indicates the wave moves downstream. When Freud's number equals 1, it is critical, meaning the wave moves at the same speed as the fluid. This is generally the case with tsunamis.
So I want to highlight something here, which is also typical of dimensionless numbers. So dimensionless numbers tell us about the ratio of one influence to another influence, right? In this case, it's inertia relative to gravity. And so very often we can then use the value of the dimensionless number, like above or below some critical threshold, not of the dimensionless number, above or below some critical threshold. Very often we see a qualitative change in behavior, right? Meaning that we will see an entirely different behavior of the system depending on the value of its dimension. And so in this case, we're talking about waves, right? And whether disturbances in a fluid or waves in a fluid travel upstream or downstream, they know that if Crowd number is exactly 1, then the wave speed is traveling at flow speed is happening. But the general thing to take away here is that with dimensionless numbers, there will often be a critical value of that dimensionless number at which the behavior of the system. So we're going to see this a lot with Reynolds number and the critical value there has to be 1. That vary depending on our definition of Reynolds number, but we will see that Reynolds number is going to be something. We'll also see this with Mach number when we discuss the supersonic, right? Their critical value is 1, right? It's whether you use sub or supersonic. But so again, it's just a general feature of dimensionless numbers. There we go. The general feature of dimensionless numbers is that that kind of. So we'll look at this Weaver number, which is up here on this list. This is the ratio of inertia to surface tension. So we'll see some examples of different Weaver number flows with droplets of water. And again, we're going to see qualitative changes in the behavior depending on the value of that. Down here, this is Weaver number 2. 7. So now we're increasing the flow rate. And we're increasing Weaver number, increasing the flow rate. And now we're not seeing, so this second drop is not coalescing, so they have enough momentum that they're not coalescing anymore. Right, so the flow rate's increasing. No, they are coalescing. So aside from interesting behavior of droplets, again, the main thing to take away here is this is essentially a behavior governed by a dimensionless number, and as we change the value of that dimensionless number, we can often see different qualitatively different behaviors. So as we're increasing the Weaver number, we're increasing the inertia of the flow, and so the surface tension effects of keeping these droplets separate and together are becoming less important, right? Relatively less important, and so we start to see these streams flowing together in a little bit. Come to that. Um, so another example, is the Rossby number. So, this has to do with, rotating flows. This is again, it's, you know, like two videos. This is a video, we're just gonna watch the end of this.
So this is the message of this number. What's the physical meaning of it?
Well, you can tell which portion of the system matters the most, and it allows us to ignore the rest.
Oh, like how I ignore my dead end for engineering.
A large fraction number tells us that the inertial and centrifugal force is dominating, and this can be in the case of a small wind sphere or a large block. For example, in a tornado.
Wait, are you reading from Wikipedia? A low pressure system, such as the atmosphere, has a low Rossby movement, and the dominating forces of pressure forces and Coriolis.
Our system is set up such that we have a slow moving flow in a tank rotating much faster at 10 rotations per minute.
This ratio of much smaller velocity to larger angular frequency tells us that our system is a low Rossby. And we see a Coriolis force is dominant in the formation of these large spirals relative to the size of the system.
So I just want to highlight something they said there. So one of the reasons we use the dimensional numbers, dimensionless numbers, is that as we observe a system with different values of those dimensional numbers, when we cross the threshold, qualitative behaviors in the flow. So waves move up or down against the flow depending on crowd number. The droplets coalesce or do not coalesce depending on the Weber number. You know, there are different behaviors depending in this rotating system depending on the Rossby number. But another thing they said there, which is really important about dimensional numbers, is that they can allow us to ignore or understand which kind of physics are important and which kind of physics can be ignored. And that's going to come into play when we're using Reynolds numbers to describe systems, which is our next. This is going to be about transition to turbulence. It's a really nice flow visualization. Showing basically what happens. We have a flow in a channel. It's going to be seeded by a dye, the rest of the flowing green dye. And the experiment is turning up the speed. And if we turn up the speed, right, keep everything else constant, we turn up the speed, rho UL over mu, so mu in the numerator or Reynolds number is higher, meaning the effects of inertia in the flow become more important. We're going to see what that does. It's qualitatively in this video. Diving. So water flows slowly. So our Reynolds number is low, right? Relatively low. Rho UL over mu is low. We can see these nice ladder streams of fluid. One way to think about this, the reason why these streams are laminar, is if there's some disturbance, you can actually see little tiny ripples. Those little tiny ripples get dampened out by viscosity because the speed is relatively low. The Reynolds number is relatively low. I mean, viscosity is dominant in this kind of system, or has a dominant effect in this kind of system. So if there's a little ripple that occurs here in the flow, it gets dampened out by distance drag. It's dampened out by viscosity. But we're going to see that as we increase the velocity, inertia takes over, and we're going to see a different kind of behavior. So now we've crossed a critical Reynolds number. And now we're seeing the formation of these vortices that are occurring behind this object. The flow of this object is still down there. This goes deep. We looked at this as an example where the early days of class of flow over a cylinder, in which case there, in the case where there were some vortices being formed behind. This is still nice and regular, periodic, uniform vortices that don't have the characteristics of turbulence yet. But we can see that as we increase the influence on inertia relative to viscosity, again, increasing the flow rate, little ripples that are in here. Right, think about it as like a piece of fluid moving faster than its neighbor, adjacent piece of fluid. Because the inertia is more important now than it was before, that little piece of fluid kind of keeps going and eventually wraps around. Right, so it's not being damped out. That difference in velocity is not being damped out by viscosity anymore. But now it's turning to control the forces that occur within the flow. So this again, the formation called the vortex street is a little bit like light lamps on either side of. We're going to next turn up the flow even more and observe what happens. Watch the force. So now we can see we're at higher flow rate, and these vortices, they're still forming, right? Still forming in this alternating pattern behind this disturbance. But now we're seeing a lot of mixing. We're seeing not only these big vortices made, but the big vortices are turning into smaller vortices. Smaller vortices are turning into smaller vortices still. Now we're seeing characteristics, starting to see characteristics of turbulence in the system, which is in a turbulent system, we have a higher Reynolds number. We have a higher Reynolds number, meaning the influence of inertia is very important relative to the influence of viscosity. And that causes vortices within the fluid to turn over itself, turn into new vortices, and create mixing across many different length scales that are highlighted. So here you're seeing characteristics of higher flow with turbulence. So here we see all of this, for example, is a big turbulent flow. Again, we're going to talk quite a bit more about turbulence as we discuss flow within pipes and flow around objects in the next couple of chapters following Rick. But the key thing here is that dimensionless numbers typically a ratio of two quantities. The Reynolds number, we're talking about inertia over viscosity. There are a couple of reasons why that matters. One is that there are often critical values of dimensionless numbers, where we see qualitative behaviors in the system. And the second is that these dimensionless numbers can tell us which physics are important and we have to pay attention to, and which physics are less important and we can therefore. We're going to return to that theme if we use dimensionless numbers. Okay. Any questions? Like I said, to start by asking you all different questions. Any questions before we move into some slides and say, let's get yeah, so we're going to define turbulence kind of phenomenologically, but based on when it's happening. Based on the characteristics of the flow. The key characteristic of the flow is not simply the presence of force, right? We said when we had the flow speed, so like really low flow speed, we saw the nice straight streams, right? But definitely not. Increase the flow speed a little bit, we saw the formation of the vortex tree. But those vortices were not turning into smaller vortices, we're not generating smaller vortices on their own. And so that's still not turbulence. The key characteristic of turbulence that we saw this in the high flow speed, the vortices or disturbances with the flow create vortices. Those vortices then create their own smaller ones, and their own smaller ones, and their own smaller ones, smaller ones, smaller ones. So in turbulent flow, you'll see disturbances across all the length scales. You'll see vortices that are really big, like the size of the object, right, at the ground of that flow, and those, and all the way down to tiny vortices. And that is characteristic. Okay, and that's what will drive the behavior of turbulence, how we analyze turbulence, the drag that's produced by turbulence, is all driven by that kind of. So that's really the way, right? Typically, if we want to know for a given system, is the system turbulent or not? We're going to look at critical values of risk. It's going to tell us, like, are we definitely laminar, definitely turbulent, or somewhere in between. But those values of Reynolds number, we're going to see the internal flow of 2300. It's kind of like seems like an arbitrary number, but it comes from empirical observation. And for external flow, we're going to get different values, like 5 times 10 to the fifth, because your critical value of Reynolds number. But again, this comes from empirical. So, yeah, so and part of that comes back to when we looked at the Navier-Stokes equations, there's Selenium prize, right? About consistency of solutions to Navier-Stokes. There are many things about Navier-Stokes equations that are not fully understood. One of them is we don't have a comprehensive theory of physics. When we're dealing with turbulent flow, we still have to know how to engineer systems with turbulence, because that's most real world big scale systems turbulent flow. So we use empirical relations. We don't have a solve. We have them properly. Question. Answer. Yeah. But I have a question. Yeah. Okay. I was watching that video. Like those. What is he kind of running with fire? Yeah. I'm wondering, is fire just like the fluid moving upward, and that's any kind of flow that's getting light at the code, or how do so combustion is beyond the scope of this class. We're not going to talk about combustion, but in the fluid, right? Let's talk about the fluid coming up off the fire. For a classic example is like smoking more like a cigarette or something, but smoke from off. That flow is driven by vortices, right? It's driven by the decreased density of the hotter fluid, and that's causing that hotter fluid to accelerate, to rise. And as it does so, and it's really clear in like smoke coming off cigarettes, you'll see it initially start out as like a nice laminar string, right? And then turn into the kind of turbulent vortical behavior structure of the bottle. That's because it's accelerating, right? Because it's going to it's accelerating, increasing its velocity, therefore increasing Reynolds number as it goes, transitioning from laminar to turbulent. So in a typical big fire, right, there's the big bonfire. There's no real laminar movement. Right? It's moving. It's so hot. There's so much buoyancy that the flow is moving so fast that essentially there's no laminar movement. And that's what you see guys. Any other questions? All right, so we're talking about mental analysis. Just I'm discussing what not to do with mental analysis. Be careful. This maybe part of the dark arts. Yeah, so this I haven't done mental analysis of this. It's great. Pretty sure this is actually dimensionless. Presumably this is dimensionless. But just because it's dimensionless doesn't necessarily. Okay. All right, so another use of dimensional analysis that we haven't, that we alluded to, but we haven't gone through in detail is the concept of modeling. So we have something that we want to understand, flow around, an airplane. But we don't want to build an entire airplane just to understand flow around it. You see it, yeah, right now. But we still would like, still would ground that to be in some of the overall state. And so model is like the world of the CFD. And so generally we're going to try to build a small scale model. But we have to understand the relevant, the controlling dimensionless parameters in order to make sure that we're not making mistakes with our models. This goes back to our governing conclusion. So the fact that we write them in dimensionless form has an important consequence, which is that if we match the geometry and the relevant dimensionless constants, then the answer to our governing equation, the solution to our governing equation, behavior of the system governed by those equations could be the same. Meaning that if I take, if I'm looking at flow around a cylinder or something, and I have a cylinder in water versus a cylinder in air, if I match the Reynolds number between those two flows, then I should see the same behavior in water as I did with a flow in air. Because we said we don't just the Reynolds number coming out of our microscopes. So we call these two concepts geometric and dynamic similarity. So geometric similarity meaning that the system has the same geometry, the same shape. Maybe different size, right? We may scale the size. But it has we have the same shape. So we're modeling both the scale model. And matching dimensionless numbers, matching the relevant dimensionless numbers, we call that dynamic similarity. And so if we do this, then we have effective models to show these two things. So the geometric means same geometry, dynamic means same. So looking at flow over sphere and water and air, but back Reynolds number, we see the same geometric similarity over spheres, all the same shape. And if we match Reynolds number, then we should see that we have both dynamic similarity, and we should expect the same solution to matrix so in this case, we're looking at drag around the sphere. You would see the same coefficient of drag. As long as we match the shape, then in these two experiments, hypothetical two experiments, one water, one air, we would end up the same coefficient of drag, same dimensions. This is when we look at that chart of drag coefficient versus Reynolds number for cylinder. This is basically the concept that we right. So those are different experiments, different size cylinders in different labs, all around the world over decades. But it all fell onto the same line, right? We would have to follow that same line with our dimensional analysis, our 5 different analysis. We can then use that result to scale up or down, bigger or smaller. So one example would be to look at a reaction vessel. Let's say we want to model a reaction vessel. And we don't want to build big giant, it's going to be some big giant tank in the planet. But we don't want to build this big giant thing. It's going to be very expensive. Just in order to understand what's going on or what's happening. And so we like to build a model of this system, but we have to figure out under what conditions do I operate this system with the model in order to understand what's going to happen and what's bigger. Another question of the model. What is in this case, we have, three relevant variables that we look at. We have the rotation speed, omega. We have the length scale. Let's say it's the diameter or something. And that's actually U1, U2, that's the kinematic viscosity of the fluid. Kinematic viscosity is U over rho. Right, U equals to U over rho. We call that kinematic viscosity of the fluid. This has dimensions of L squared. Same as the part about this is should be but for now U, not B, it's U, it's U. But we have more letters. It's not the letter. In some cases, it's a little from B, but it's okay. So if we know that, let's see, so I guess given in this problem is that gravity and the character and the flow, inertia, and viscosity are going to be important. So this is going to match our Reynolds number and our proof number. This is given in the problem. Match Reynolds. So the velocity of the system, in this case, the velocity U would be roughly approximately the rotational speed omega times length. So this would have dimensions of the rotational speed would be like dimensions of 1 over time. This would have a dimension. And this would define basically how fast is the fluid moving is spinning around. So using omega times L. U is U over rho. Definition of kinematic viscosity. And so to match Reynolds number, we end up with this condition, right? Reynolds number is U L. We write Reynolds number as rho U L over U. But the ratio of U to rho, right at the U, max stop. So this is U L over U. And we said that U was omega times L, so we end up with omega times L squared. And so to enforce the Reynolds numbers, we're going to say that omega 1 L1 squared over U1, right? Reynolds number 1 should be equal to the Reynolds number for. So our model Reynolds number, Reynolds number 2 should equal the system Reynolds number. That's one condition that we get from to enforce dynamic similarity. So our Froude number will write as U squared over GL. And so we end up with this condition that omega squared L1 over G will be omega squared L2 over G. Now we have these two conditions, and to enforce dynamic similarity, both of these things have to be true. Both Reynolds number and the Froude number. We have the dynamic similarity means that all dimensions are constants. All the dimensions of this number can system are the same in the model and the system. So now we can use some algebra to work this out. So G drops out from the Froude number matching. We end up with this expression. Omega 1 squared over omega 2 squared is also Froude 1. From Reynolds number matching, we then plug that into our Reynolds number expression, and we develop this expression, L2 over L1 to the 1.5 to 2 over 3.1. And so we now have a condition on, L2 is L1 times, this, 2/3 power of the ratio of the viscosity. So if the, assume, for example, fluid 1 is water, right? So let's say the, reaction vessel that we're trying to model is, gonna be, a stir tank of mostly water. So we can use that. And then, we're gonna model it, we're gonna attempt to model using glycerin. Glycerin has a high viscosity. So we can now see, how big we need to make the, what the ratio of the systems are. So, the ratio of viscosities is 1,000 for, water to glycerin. And so our L2 would be 1/100th size of the molecule. So this is telling us that, it's telling us that in this system, if we were to, keep the dimension, keep the geometry the same, shape the same, how they have same orientation of the paddle, relative to the bottom, and so on. But make the system 100 times smaller and use glycerin, then we should see the same behavior. That's weird. This came from forcing dynamics. So we do the same thing to figure out what the operation speed needs to be. By again imposing our conditions of dynamic similarity, and figure out in this expression that's omega 2 or given speed of our model with omega 1 times the ratio of the stop power. And we can see that in this model system that we're going to run with glycerin, we want to see the same behavior, 100 times smaller, now we're getting velocity 10 times faster. Do that, then the behavior in this system, this small scale system, should exactly mimic the behavior. So another example is submarine. Let's say we want to build a model of submarine. In this case, the only thing that's really important here is the Reynolds number. The submarine is completely underwater. We're going to assume that there's no impact of gravity on the flow around the submarine, which is the body completely immersed in water. And so we want to match. Let's say we want to build a scale model or something that cameras going on. We're going to try to match Reynolds number. That's all. Reynolds number for the full scale system to be Reynolds number model. Let's say we want to build a system again that's 100 times smaller. So let's look at what's. Let's assume that we're going to test it in water. Water is relatively cheap. So we're going to test the water up. A 1/100 scale submarine is still cheap. So we're going to still want to test this in water. So we do that. So U1 now needs to be 100 times U2. So if U1 is 20 meters per second, we'll see a submarine, something like that. Then U2 has to be 2,000 meters per second. It's the case where dimensional analysis kind of speed of sound in water is about 1,500 meters per second, so now and then you don't have something in the craft. So now we weren't considering modifying before, but now we no longer match it. This one not so we'd have to probably go back and need right this is by a big tank yeah, we're going to change stuff. So if you look a little bit careful, right? So it can tell us sometimes we get mentions that are nonsensical. In this case, the key thing to find here is that we did our model, right? Or we did our model calculation we end up with a value where, so we did our model calculation based on dynamic similarity of Reynolds and relative variable. But when we end up with our new system, we saw that we now don't have dynamic similarity. This is another concept. Actually, we use glycerin, then that would actually make it worse. But now our cells would get up on the lower the cost. So this is another. So something to be careful about. And this actually gets to failure of modeling, famous failure of modeling, which was the Wright brothers. They famously did a large number of wind tunnel tests to try to determine the optimal shape of a wing, right, before they made their right fly. It didn't fly that well. Right? We flew well for the first airplane. So it's credit too, but their modeling was a little bit suspect. So they built small scale models of their wings, right? Of different wing shapes. They tested them in a small wing. So they enforced geometric similarity. They had the same shape, the same wing shape between their model, between what they're considering building. But we were doing it in air, and their system was running at about the same speed that their airplane was going to fly at. So what's the problem? What didn't they map? So same speed, same viscosity, right? Same material on a smaller scale. They should have changed velocity. And so what did they not consider? The length scale was the same. Reynolds difference. Yeah, exactly. So if they keep you the same, or roughly the same, and viscosity the same, they're using the same material, it changed less. Then they were not enforcing dynamic similarity. Right. And so their results famously predicted much better performance. They found airfoil tapes that performed really well for a low Reynolds number, but not that well. So one of the reasons why. Another has to be drag. We'll talk about that. But modeling. All right, so I just want to return here. We started by this section by saying that by using this Taylor, P.I. Taylor atomic bomb estimate as an example of the power of dimensional analysis, right? So from photographs that were publicly available in Life magazine and some dimensional analysis, Taylor was able to figure out the power of the atomic bomb data application. And T.I. Taylor, if you look around fluid mechanics, his name is all over the place. So Taylor dispersion has to do with how flow can cause effectively receiving rotating cylinder flow. There's a Taylor number. Having like a dimensionless constant named after you is, I don't know, maybe the best honor the fluid mechanician can ever receive. Taylor has sort of issued that. And many others. So it's going to Wikipedia and look at T.I. Taylor, you end up with like a node for all of these things, right? All of these different complex, it's an interesting phenomenon. So it was, I don't know, did a lot of great work. So we're going to yeah. Okay, so we had then we have like a scalar multiplier and all of them like some of them are networks. Yeah, so it's both. Any already, so we could take the square root of this and still be dimensions, right? And actually look probably a little bit nicer, right? There'd be omega r squared over u, that would be a different answer. And yeah, So that, any operation that we apply to all terms would be mentioned, right? And then the reason why there's a constant out front for, didn't take care of this thing is by condition, right? So, I have looked at exactly where this came from, what the table we're going to describe, the problem with some reason that they could. And because if somebody said it should be this way, we're now stuck with that. Okay. So the question was, what was the yield of this Trinity bomb test? This is the thing that Taylor was trying to figure out. I was classified at the time. He put out a paper on this in 1949, and the test was done in 1947. So yeah, really put out this information they didn't want to keep it out. But so photos have been published in Life magazine, and we saw the video, and these photos have time, and they have one scale, which like compared to the 60 here, I mean, you probably not do. But from that, we're jacked out. Well, I know a thing or two about dance, and he's been conducting somewhat related research. So he, it's just a fun, did dimensional analysis of this system. So he assumed that the energy release depends on the radius r of the shock wave, and sometimes the density of the atmosphere rho. This is more or less because, again, he was doing some related research on shock waves. So he didn't just get this out of thin air with T.I. Taylor. He was also doing some work in a related area. He kind of knew that this should be the right form. And so we can follow in its footsteps and do the same thing. So if we apply the pi theorem, we look at the dimensions of all of the variables. Right, so we have M, L, and T. Right, so we have three fundamental quantities, right? Three dimensions. We have four variables. So 4 minus 3 is 1. So we should have one pi group driving the system. And 4 minus 3 is one dimension group. That means shock wave expansion is described by a single constant. All you have to do is figure out that single constant. You can do it in a policy. You don't have to do it with the policy. Use the policy system. And then use the known density of air, time, and length scale that you need from the images. Figure this out. So through dimensional analysis, any kind of techniques that we learned a couple of days ago, drive pi 1, a little more complicated than what we saw before. T squared u r over rho. And so this predicts that r should grow as t to 250. So in the video, this is still going now. Then I can plot. So if you were to take those photos from Life magazine, plot the rates against the Google route, figure out like how many feet is 1 millimeter or something on the ruler, and end up with the radius of that blast as a function of time. Right? It's going to be measuring those photos. Then you end up with the shape. Your model predicted, or the pi analysis predicted, that r should go as 250. This thing is constant. Energy is whatever the energy was of the explosion. Density is this density of air. So we should see. So that helps from the relation between r and t. Back up. So we now have confirmation that this looks reasonable. We can now back out what the energy is. Right. So we now look at these holes. Now you can run some like laboratory scale experiments, non-involving nuclear explosion, estimate what the value of pi is, and now back out what the value of P was. Right. And so Taylor came up with an estimate, and he put error bars on it. He didn't go experimental with it. 16.8 to 23.7 kilotons. The actual number is 20. Yeah. Again, they figured out on this photograph. All right, so that's where we're gonna end our discussion of, dimensional analysis. Time for a call break, or this spot. When we come back, we're gonna use, essentially up to this point, I just wanna direct this from here. Up to this point, we're developing tools for us. Right, we've developed tools to understand control volumes, tools to understand different equations, describing fluids, tools to understand dimensions, and what we can learn from that. When we come back from break, we're gonna start applying those things in earnest. We'll start with internal flow, like flow through high. A great break. Control.